All right, hey guys, welcome back to the Mathematics of Data Model, Lecture 14. This is a Northeastern University course and called CS 2810. Now, today we're going to go over optimization and some basic matrix calculus notations, as well as this algorithm called gradient descent. Gradient descent. So let's get started. Professor Wu. Okay, so today we're going to learn some basic optimization notation. Specifically, this notation here. What does it mean when you see this? Well, first of all, this is a function. So, what this is saying is that we want to find the x such that this expression is minimized. So, this expression is just really this function here. Therefore, the x that will make that's that where this function is smallest will be right here, right? This is the smallest value. So what it's asking here is what is the x value such that if you plug it in, it will give you the smallest possible uh, output. Now, from basic calculus, right, we learned that the lowest point is where the slope is zero. So the easiest thing we can do is just take the derivative and set the derivative to zero, which would tell us that x is equal to 2. You can see x equals to 2 is a good spot, right? Now, now this right here is the standard way we learn in calculus how to find the minimum or the maximum of a problem. Now, in machine learning, we very often have to minimize or maximize problems. So, one example is let's say we are going to build a fence in a rectangular field, right? We want a rectangle. And we look at the field from above, the cost of the vertical side, right? So these two sides are $10 a foot, $10 a foot. The cost of the bottom is $2, and the cost at the top is 7. Now, if we have $700 total, then what is the maximum enclosed area? What is the maximum area? So, for this, we know that if we have $700, $10 times y, which is the number of the side fence, plus 10, which is 10 times the number of side fence, plus 2x. There's $2 for the x and $7 for x here. So we know this relationship from our description. Well, we simplify this. It's just 20y plus 9x. We solve for x. This is x. Next, we know that the area is x times y. Therefore, we know what x is. So it's just x times y. And the problem we want to solve is we want to find the y such that this area is maximized. Okay? So the problem we just saw can be formulated this way. Now, this is a very simple model of the of a fence setting. In various data science projects, the model you will use will be significantly more complicated than this. But the idea is the same. Essentially, you're trying to find y to maximize something like an area. Once you have y, right, you can plug it back in and get x. So with these, it's actually pretty easy to find a derivative, right? You can find a derivative, set it to 0. In fact, with anything with a single variable like x, which when x is just a single variable, it's pretty easy to find the derivative. However, what if x is a vector, right? In this example here, x is a vector. So if x is a vector, then how do you find df dx? So hopefully you've learned this in Calc 3. So in Calc 3, you essentially learn how to do this. But you probably didn't learn it with matrix notations. So today we're going to review a little bit of Calc 3, multivariate calculus, and combine it with how you will represent it in matrix vector format. Okay. So there are 4 steps to solve like the derivative of a function that has a vector as an input. Step 1 is to multiply out the entire matrix. Then you calculate the derivative one variable at a time. And then if you can identify some pattern which you can use for the future. So let's look at a really, really simple example. Over here, what is the derivative of f with respect to x? Well, we know given that y is this and x is equal to this, the step 1 tells us we should just multiply them out. Therefore, let's multiply them out. If we do that, that's 2x1 plus x2. Okay? That's step 1. In step 2, we take the output of step 1 and take derivative with respect to one variable at a time. So these are the vectors, right? You would essentially get the derivative of df dx1, df dx2, align exactly the same orientation as the original vector. So what is the derivative of this with respect to x1? Well, it's going to be 2, right? And then what is the derivative of this with respect to x2? Well, it's going to be 1. So df dx is just 2, 1. Yeah. Now that we know what this is, notice this is the derivative df dx, and that this is equal to y. Okay? So the pattern here, I hope you can see, is that df dx, right, is just y. That is, if you take the derivative of this expression with respect to x goes away, and you only have y. And the reason why that's the case was everything we did here. Okay. So right now we have a vector of length 2. But you can imagine if we have a vector that's longer, 100, 1000, right? And then you take the derivative, well, it's still going to be y. It's just y now is the size of 1000, right? So even though you can have a lot of different variables instead of just 2, you can have 1000. When you take the derivative, the result is still the same. Okay? And we learned from the previous class, if you flip x and y, it doesn't matter because they're equivalent. Therefore, the derivative of them is still the same, exactly the same, even if you flip the order of x and y. Okay, so now I want you to pause the video and give it a try to see if you can find the derivative of this, which is you want to find df dx. Okay, pause the video, see if you can do it. So we'll move on to show you how to do it. Now, to find a derivative for this function, the first step, as I told you, is to multiply them out. Therefore, this is x1, x2, x1, x2, and here's a. Okay? So if we multiply them out, it becomes a quadratic equation. Now, all we have to do is take the derivative with respect to one variable at a time. So df dx1, so these are the one with x1, and this cancels out. So that's 2x1 plus x2. What about df dx2? Well, you have these. So x2 is going to cancel out, and this is going to be 4x2, right? So that's how we got this. So right now, we went from f of x, and when we got df dx. After we have df dx, right, the pattern here is not as obvious. All right, what is the pattern? Well, we can rewrite this split them into matrix vector format. And notice we can once again split this into this and this. Because if you add them together, right, they're going to equal to this. Now, what's interesting here is this is A transpose, right? This is A transpose, and this is just A. So that's the pattern that when you take derivative, it's A transpose A X, right? Specifically, if you have this expression, X transpose AX, and you want to take the derivative, it becomes A transpose A X. So this is the general pattern. So if you remember this, next time you would not need to have to go through this whole thing. So the derivative of this is this. But if you forget, you can always just multiply them out. Just always multiply them out and then do them one at a time. Okay? Now, specifically, this plus this, if A is symmetric, then you have an even simpler form, which is just 2ax. So that's how you take the derivative for this right here. All right, let's do even more practice. You want to pause the video, see if you can do this right here. Okay, now with all the properties we learned from last class, hopefully we can apply them. Now, we can split this into the left and right. When you have a square, what it means is you write it twice, you put a transpose here. Now, if you just multiply them out one at a time, you'll get this. Okay? So, well, how do we solve this? Well, the way we can solve this is essentially take the derivative of this and then set it to 0, the derivative to 0. So we just simplified it. Next, we want to take the derivative. So what is the derivative? Well, let's see. Well, the derivative is right here. It's right here. So you see that when, because this is symmetric, when we take the derivative of this, it just gives us 2. And then this cancels out because there's no x in here. And over here, when you take the derivative, x cancels out. And then you end up with this expression. Now, this right here is slightly different from what you're used to, right? We were saying that x transpose y dx. If we take the derivative of this, it will give us y, right? Now, what we have now is we want to have dx with 2x transpose a transpose y. Now, the thing with this is y times a transpose is just another vector, leading us to a 2x transpose z. And once we reach this point, it's pretty easy. The solution is just 2z when you want to take the derivative. Okay, so that's how I was able to get the second term. Now we just set this to 0, right? If we set the derivative to 0, then what happens? We can move this over there, so it's on the right side, and then 2 cancels out, right? So 2 cancels out. Now, over here, what we could do is multiply by A transpose A inverse on both sides here as well. Now we got X. So notice, even though we were trying to solve this problem here, we end up solving the same problem of AX equals to Y. Because this right here is the solution. This is that pseudo inverse, right? So this is the pseudo inverse. So this is why I was telling you that when we are solving ax equals to y, it's actually equivalent to minimizing, right? You're trying to find the x such that the error is minimized. So, yeah, You may remember this is the pseudo-inverse solution. So when you solve a pseudo-inverse, or when you're solving the minimization problem, you got the exact same result. Okay, so far, when we try to solve a problem, right, minimize x some function, when we're solving this, we know that if we take the derivative and then we set it to zero, right? If once we set it to zero and solve it, we know the optimal. But in those cases, it's required that you can set the derivative to zero. But there are many functions that are too complicated for you to set the derivative to zero. For example, over here, you can try taking the derivative of this function and then try to set it to zero. But it will be kind of complicated. So for the cases that you cannot take the derivative and set it to zero, how do you solve a minimization problem? Right? So the way we solve minimization problem when we cannot take the derivative is called gradient descent. Okay? So today, now that we've gone through the concept of minimization, we want to see a general way which we can solve for the optimal solution. So first, let's go over the concept of derivatives. You may have learned in calculus that derivatives are really just slopes, right? So if we have a function, right, x squared, the function tells us that at a given point x, what the y value is. What is the f of x at this given point? Right? So that's what the function tells us. But what does the derivative of the function tell us? Well, it tells us the slope. And what that means is, let's say you find it here. The slope is going to be positive, meaning that as you start, means that the function is going up. As you go this way towards the right, or as the number of as the x value increases, the function is also going to increase. That's what that means when you have a slope that's positive. So it tells you that as you walk towards the right, or as the x value increases, it will push the function up. That's what a positive slope means. Conversely, a negative slope, right, over here is a negative slope. So this is negative, this is positive. It means that as you go towards the right, the function is going to go down. Okay, so that's what derivative and slope means. So if you know at a given point if the function is going up or going down, the conclusion is that even if you can't set the derivative to zero, even if you can't do that, you can always pick a point. And then by looking at the derivative of this point, you know which way to walk towards the minimum. So by looking at the derivative, you know that if it's positive, well, positive means that if you walk this way, it's going to get bigger. And if you walk this way, it's going to be smaller. So by looking at the derivative, we know that we should walk towards the left, maybe over here. And then over here, you want to walk towards the left again. So if you do this over and over and over again, you will be able to reach the minimum. So let's look at this toy example, which is a parabola, right? So obviously, we can get the derivative. We can get the derivative of the parabola and set it to zero. So that's not a problem. But we're gonna pretend we can't do it because that's the whole point. There are functions out there we can't just set the derivative to zero. So for those cases, how do you deal with it? Right? Well, the idea of this algorithm, I just described it to you, is that we study the way um, we study at each point, we look at the slope. And by looking at the slope, essentially we would know that if we move towards the left a little bit, we're going to get a value of f of x that's even lower. Okay? So let's walk through this. Let's say there's a person. Currently, you can randomly pick anywhere, but let's say this person is standing at x equals to 2. Okay? So this person's here. Now, let's say we have x. Well, I call it x, but it's alpha. Yeah. Let's say the current location is 2, right? Can we subtract something so it will give us the next location such that it's closer towards the minimum? So how do we know what we can subtract here? Well, it turns out that, but just by looking at the derivative at this point, if we look at the derivative, it tells us exactly which way to go. Now, the derivative of this function is 2a. Okay, so how do we look at the derivative and for it to tell us which way to go? Well, it if the derivative, like I told you, if it's a positive value, right? If we plug 2 in here, it gives us a positive value. What that means is as you walk towards the right, you're going to get higher and higher. Therefore, you want to do the opposite of the derivative. So if you have now the and then the opposite of derivative, which is negative derivative, it will tell you that you want to walk towards the left by 4. So you want to walk left by 4. Okay? Now, yes, we did walk towards the right direction, but the perfect location is at 0. So we were overshooting our target. Not only did we walk left, we walked way too far left. So in that case, the f of x, there was no benefit. So so we know we're walking the right direction, but we walk too far. The solution is to take smaller steps, right? So instead of multiplying by 4, we take the derivative and multiply by a smaller constant. So a fraction, 20% of how much you walk. And now, instead of walking the full 4, it would just walk a little bit. Okay? So in general, you can imagine if you walk too far, you can get even larger values. So if you walk small enough, you're always going to be able to get a smaller value. Okay? So so that's a general idea. Whenever you're using this algorithm, and you need to pick your own step size. And this is a step size. And if your step size is too big, you might very well overshoot, right? You might be here and your step size is too big. So now you get a larger value. So the key is to take a smaller step. So this is the step, and we're going to take a percentage of that step, which I picked 0.2. Again, you can pick however size you want. You just got to make sure you keep going downward. Now, if we do this whole calculation, x now minus something. After minus this, now we get 1.2. Okay, so we have effectively walked from here to here. With this time, we did not overshoot. We just took a small step, and we are heading closer to the optimal solution. Okay, so the point here is you have this and you have this, right? If you take the current location where you're at, right, which is 2, if you take and subtract the derivative times some smaller step size, you should little by little walk towards the optimal solution. Okay? If we repeat this process, notice we're getting closer and closer and closer. And this is the algorithm for gradient descent. Now, in case you were wondering, what if we start on the left side? Well, if we start on the left side, then the gradient would be minus 4. Now you have minus multiplied by minus, which gives you a plus. So this tells you it's still telling you to walk towards the right. Previously, it's trying to walk towards the left. But over here, you want to walk towards the right because the sign flipped. We can apply the same idea in higher dimensions. So over here, this is the data, and now we're trying to minimize this. Now, we did this practice. So the minimization of this requires us to first take the derivative. The derivative of this is simply x times A transpose A. Okay, what is A? What is A transpose plus A? Well, it's just 2, 1, 1, 4. Okay, so now we actually know the derivative for this. So if we start at some point, x0, and let's say x0 is 1, 1, we start from this point, right? X0. What we want to get is the next point. Therefore, it's x0 minus a dot df dt, df dx. Okay, so x0. So we plug this right here and x start, which is here, and this allows us to essentially take one step closer. So what we were doing here was just one dimension, right? However, when we are dealing with vectors, right, instead of numbers, then we're in a higher dimension. And you can solve the higher dimension equivalently using the gradient descent algorithm. Okay. Now, if we take one step, another step, another step, you can see that it's going to get incrementally closer towards the right solution. Now, you may remember from the one of the previous classes where we're trying to solve regression. And the idea of regression is that you have some x value and that you have some y value. And we want to find a function, f of x, such that when we plug x, it gives us the best estimation of y. When we plug x, it gives us the estimation of y. Well, since if we don't know what f of x is, right? In these kind of problem, what we do is we just make assumptions that f of x is just a combination of a bunch of other functions. So, for the sake of this example, let's assume it's two functions, f1, f2. So, f of x is a combination of f1, f2 times some constant. That's the assumption here. And if we let f1 equals x squared, f2, then the function that we're trying to solve is right here. So in this function, we don't know what a1 and a2 is. So if we were able to find a1 and a2, that would essentially tell us the function that allows us to predict y value given x. So next, now that we know what the function is, we have 4 points, right? x1, x2, x1, x2, x2, x4. So we have 4 points. Well, if this is the function, we can just plug the 4 points in, x1 in, and that should try to predict y1. If we plug x2 in, that should try to predict y2, right? So we can just plug the number in and rewrite it into the matrix format. So this right here is actually not right. It should be, yeah, no, this is right. Now if we plug it in, this is what it's going to look like. So at this point, we can reformulate this into vector matrix format. Right. Once we have in this format, this is the standard problem we have been solving the whole semester. A times x equals to y. Now, previously we learned how to solve this. To solve this, we just multiply by its pseudo inverse. This whole thing, right? After we multiply a pseudo inverse on both sides, we can now solve for x. So this is how we are able to solve x, like previously. So all these is just review for what we did previously. But now, previously we were trying to solve this, right? What I'm trying to tell you is that this problem is equivalent to this problem. And I showed you previously how that's the case, right? And now I also showed you how to solve this not with a closed form solution, but with gradient descent. So you can essentially solve this using gradient descent by taking the derivative. Okay. So let's. This is the last problem. This is x and y, and we want to find f of x. So first, solve this problem again. Now you're going to solve this problem using the pseudo inverse method. Once you get the solution for the pseudo inverse method, right, you want to solve this problem. This problem, I told you previously, is equivalent. But I want you to solve this problem using gradient descent. Instead of just getting the solution, I want you to write the code to essentially program it. You want to program it to step by step reach towards the optimal solution. So to solve this, you want to find the derivative. You can set eta to 0.1, and then you want to do the gradient descent algorithm. So that's it for today. I hope this is not too complicated. Well, we'll see each other next time.